So we've learned about the antiderivative to a given function. So let's say you have a function like this. The antiderivative is just the function whose derivative is equal to the given function. And this is a really important concept in calculus, and it's kind of forms half of the class. In half of the class you learn about the derivative, right? In the second half of the class you learn about the antiderivative. So it's kind of like you learn how to find a derivative, and then you learn how to undo it. You learn how to go backwards. The derivative and the antiderivative are kind of inverse operations of one another, just like multiplication and division, or addition and subtraction, exponents and roots. There's derivatives and antiderivatives. And we learned in the last video that there's actually, if you have a given function like this, there's actually an infinite number of antiderivatives, but they all differ by a constant. So when you find the antiderivative, you always add a plus c, okay, to get an expression for all the possible antiderivatives. Okay, now if I want the antiderivative, though, to pass through a given point, then there's only one antiderivative that will actually pass through the given point. Okay? And so what we're going to learn here is how to find that one antiderivative. And this is why it's important to put a plus c. Okay? So let me show you what I mean. It wants us to find the antiderivative to this function that passes through the point 435. Okay? So what I'm going to do is I'm going to find an expression for the general antiderivative. We don't want that. Just f of x, capital F of x here. Maybe I'll cross this out. There we go. So I'm going to use this power rule that we learned. So this is a constant multiple. Then I have like x squared over 2. That's the power rule for this. And then we have 2x. So the derivative that gives you 2 would be 2x. But we also have a plus c there. Okay, so I could simplify this a little bit and write it like this. Okay, so this is my general antiderivative, and there would be an infinite number of antiderivatives for any given value. Or once you choose your constant c, you would have an infinite number of antiderivatives, and one for each value of c. So, but what I want is I want the antiderivative that's going to pass through the point 435. So what I do here is I plug in for my x's, I plug in 4, and for my y value, or my f of x value, I plug in 35. And then what I can do is I can solve for c, and that's going to be my constant for the particular antiderivative that gives me, the particular one that's going to pass through this point, or that'll give me 35 when I plug in 4. Okay, so I'm going to put in 35 is equal to 5 halves 4 squared minus 2 times 4 plus c. Okay, so this would be 35 is equal to, this would be 16, so that would be like 40, and then multiplying that together gives me 8 plus c. So 35 is equal to, this would be 32 plus c. So it looks like my c is equal to 3. So my specific antiderivative that passes through that point will be, now I plug the 3 in for this. So it'd be like 5 halves x squared minus 2x plus 3. And that would be the antiderivative to this function that passes through that point. And if I plugged in, let me plug in 4 into here, I would get 5 halves 4 squared minus 2 times 4 plus 3. And then this would be like, this thing would reduce down to 40, this would reduce down to 8, and then you'd have the plus 3, and that would equal 35. And so if you plug in 4, you get 35. So this is the antiderivative, the specific one that satisfies this condition. So this is actually known as an initial condition. So basically, when you have a derivative, there's problems where you're given the derivative and an initial condition, and an initial condition is just an ordered pair that you want the function to pass through, and then what you can do is find a specific antiderivative that satisfies that initial condition. Okay, so now let's use this in a situation we're very familiar with to see how this works. Okay, so we're told here that a rock is thrown off of a 500-foot cliff at a rate of 25 feet per second. Find functions for the position, velocity, and acceleration of the rock at time t. So here's the idea here. I know that the acceleration at time t is a constant. Okay, and since I'm dealing with feet per second here, the velocity would be negative 32 feet per second squared, and that's the acceleration due to gravity, right? Okay, so that's a constant. Now, the velocity here is just the antiderivative of the acceleration. And so the antiderivative of this would be negative 32t plus c. So you have this, this is why the c is important here. To get the velocity function, we need to find the specific antiderivative that's going to go through the initial condition, where we're told here that the velocity, the initial velocity, so the velocity at time 0 is a positive 25. Positive because you're throwing the rock up at this speed. So this is like the initial condition for velocity, or initial velocity. Oop. Or we could say the initial velocity, V naught, is 25 feet per second, right? The initial velocity is, you can think of it as being ordered pair that the antiderivative has to pass through, right? So now I can plug this in. So when I put in 0, so this will be 20. When I put in 0 for t, I get 25 for my initial velocity. And this is pretty easy because then I'm just given that c has to equal 25. And so now I know my velocity function is a negative 32t plus 25. And so now I have, this is my acceleration function, this is my velocity function, right? And so now I can find the position function, which we'll call that the height function. And the height function is just going to be the antiderivative of the velocity, okay? Because the velocity would be the derivative of the height. So we find the antiderivative, and it'll have an initial condition at time 0. Okay, this is being thrown off a 500-foot cliff. So at time 0, the initial height is 500 feet. So you can think of this as the initial condition, or initial height, or h naught is equal to, in this case, 500 feet. Right? That's an initial condition. So So taking the antiderivative to this, what I'm going to do is, this is like a constant multiple, I'm going to use the power rule for this, okay, and then this will be just 25t, and then I'm going to add a plus c. So this would be like my general antiderivative, but then we have this initial condition. So when you put in 0 for t, and this, let me say, I can simplify this here as this will be negative 16t squared plus 25t plus c. And then when I put in the initial condition, so I put in 0 for t, I get 500 for my height. So we got 0 squared plus 25, 0 plus c. And then here we can see that my c is equal to 500. That's my initial height. So my final, the specific antiderivative for this initial condition would be negative 16t squared plus 25t plus 500. And so this is what it asked. It wanted the height function, the velocity function, and the acceleration function. Okay, and so we start with the acceleration, which is constant. We do the antiderivative, plug in the initial condition, and we get the velocity function, right? And then we do the antiderivative, plug in this initial condition, and we get the height function. Okay, and this can be, you can use this then, let's see here, let me get a sheet of scratch paper. Ooh. Oh, my chair just fell apart. Huh, that was weird. Okay, the chair I'm sitting on. Okay, so what I was going to say is if you're given like, initial velocity of v naught and an initial height of h naught, then the height function, we've learned this, is negative 16t squared, and this is when this is feet per second and this is feet. Then we have this plus v naught t plus h naught. This is exactly what we have here. This is your v naught. This is your h naught, right? And then this comes from the acceleration due to gravity. So this is a constant. It is not the acceleration due to gravity, but it is half of the acceleration due to gravity. And the reason it's half of that is because you have to use the power rule, right? When you come here, this power rule is why this is always half of the acceleration due to gravity and not the acceleration due to gravity. Okay? And this is the initial velocity, because when you use this initial condition, you get a v naught for your c. This is the initial height, because when you use that initial condition, you get the height there. Okay? And so this formula, which I think we've introduced earlier, or you have seen at some point, this is why it is that way. It's because we're starting with a constant acceleration, because the only force acting on it is the acceleration due to gravity, and you have these initial conditions, and you're doing the antiderivative and solving for the initial conditions. Okay? So I'm going to finish with one last problem using these ideas, and we're going to just do a bunch of stuff here. So we're going to do the same thing. A rock is thrown off of a 500 cliff, but now the cliff is on the moon, but we're going to throw it at a rate of 25 feet per second, And what I want to know is how high does the rock go, how long is it in the air, and how fast is it moving when it hits the ground. Okay? And the thing here is it's on the moon, and now the acceleration due to gravity is no longer 32 feet per second, it's only 5.3 feet per second. It's a lot less on the moon. Okay? So my A of t would be the 5.3, and then my, and we can think we got these initial conditions. Again, 0, 500. This is the velocity. This is the height, or position, the initial height. Okay, so my V of t would just be 5.3 t plus c, and we can see that when I plug in 0 and 25, my c is just going to be 25. So I can do V of t is equal to 5.3 t plus 25. So that's my velocity. And then now I can find h of t, which is the antiderivative to this, and that would be 5.3, and it'll be t squared over 2, so I can divide that in half and get t squared. This would be 25t, and then I'd have a plus c, but then we plug in this initial condition, put zeros in here, 500 for height, and we can see that the c would be 500, and now I can find h of t is equal to, and 5.3 divided in half would be, is like 2.65. So 2.65 t squared plus, and that's like your 16. And you know what? This should be, all this time, this should be negative, shouldn't it? Sorry about that. That's negative. This is negative, so this would be negative. And then we have 25t, and this would be plus 500. And this is my height function. So notice the height function is like this parabola going down, where this is like 500, and this is the highest point, right? And so what does it ask us here? How high does the rock go? So that's the highest point. We want to find that. Okay, we want to know how long the rock is in the air. So we want to know at what time it hits the ground. And then we want to know how fast is it going when it hits the ground. So to find this height here, this maximum height, I'm going to use this fact that this is like the opposite of b over 2a. That's the where the vertex here, the t value is the opposite of b over 2a, and then the height would be plugging that value into here. So this would be the opposite of 25 over 2 times a would be negative 2.65. So this is how long it takes to reach its maximum height. So negative 25 divided by, and this would be just negative 5.3. And I get that this is approximately, I'll round to 2. We'll say 4.72 seconds. So this is how long it takes for the rock to reach its height, but this isn't what it's asking for. It wants to know how high does that rock go. And so we can plug that in here. So we can plug it into this to find how high the rock goes. And so when I do that, that would be negative 2.65, 4.72 squared plus 25, 4.72 plus 500. So now I'm going to plug it into here. So negative 2.65 times 4.72 squared plus 25 times 4.72 plus 500. And we see the rock is going to go 558.96 feet high. So it travels up above the top of the cliff about 58 feet. Okay. Now it wants to know how long is it in the air. So what I'm wanting to do is I'm wanting to find this root. So this is like a quadratic equation that's going to have two roots. So what I'm really doing is I'm trying to solve this equation, and I want to get the positive root. So I could write this down, negative 2.65t squared plus 25t plus 500 is equal to 0. So now I'm going to use the quadratic equation to find these two roots. So the opposite of b, so negative 25 plus or minus the square root of 25 squared minus 4ac, so negative 2.65, and c is 500, all over 2 times negative 2.65. So now I'm going to plug this in here. And so I'm going to get, well, maybe let me write my two roots out. So this would be negative 25 plus or minus, and let me figure all this out. So 25 squared plus 4 times 2.65. Oop. Let me do that again. 25 squared plus 4 times 2.65 times 500. I get all of that, and then I'm going to take the square root. And so this is approximately here 76.97. all over 2a, so this is like negative 5.3. Okay, so now let's plug in the plus and then the minus. So minus 25 plus 76.97 divided by negative 5.3, and I get like this is the negative root. I get like negative. I get a negative 9.8 seconds or so. So now let me plug in the positive root. So this will be a minus here. And it's like 19. So boy, it's in the air quite a while. So I'm gonna choose the t equals 19.24 seconds if I round to 3 decimal places or 2 decimal places. So it's in the air for like about 19 seconds. Wow. And then it hits the ground, and now we want to know how fast is it moving when it hits the ground. Well, this is a matter of plugging it into the velocity function, right? So let's do that. V of 19.24, and I'm going to get negative 5.3, 19.24 plus 25, and I'm squeezing that in there. Sorry about that, but you know what I'm doing. So what do I get? Negative 5.3 times 19.24 plus 25, and I get a negative 76.972 feet per second. Negative because it's going down, and this is the speed at which it hits the ground. So the answers then are this one, and that one. And so you can see then this is a application of the antiderivatives. Now you could have done this with information that you've learned in the past, that this is half of the acceleration due to gravity, that's the initial velocity, that's the initial height, and then you could do all this, but this is showing you how if you were given a different sort of acceleration, maybe one that's not constant, right? This is, you could find the antiderivatives, plug in the initial conditions, and go from there and answer these sorts of questions. So a nice application to finish this section on the mean value theorem.